An online platform for sharing and executing Python code, Google Collaboratory Colab uses this Python code. We import the required package drive from the google.colab library, which allows Colab to access Google Drive. Using drive.mount, we mount Google Drive to the Colab virtual machine. Within our Colab notebook, we can access files and folders from Google Drive. As a next step, we specify the folder name in our Google Drive where the assignment folder has been saved. This allows us to access and work with the assignment files easily. A folder name cannot be empty using the assert statement. In the Colab VM, we use the sys package to append the path to our assignment folder to the Python interpreter after mounting our drive. With this feature, we can import and work with Python files within Google Drive. Finally, we run getdatasets.sh by using the bash command after changing to the assignment folder in our drive. If the dataset does not already exist in our drive, it will be downloaded with this script. There are many computer vision tasks that use this dataset. This code allows us to access and work with files on our Google Drive within the Colab VM, as well as ensures that we have the necessary dataset. In the first line of the code, Torch, Torch Vision, NumPy, and Matplotlib are imported. Almost all Python machine learning and data analysis tasks use these modules and libraries. Sent Matplotlib inline allows plots to be displayed in Jupyter Notebook cells via special syntax. The code then sets up default settings for the size and interpolation method of plots using plt.rc params. After that, the code defines a function called showImages that takes a batch of images as input. It calculates the row and column sizes for the plot from the square root of the number of images reshaped to a two-dimensional array. Matplotlib.gridspec is used in the next few lines to create a figure and a grid of subplots. In the following step, a subplot is created for each image in the batch, and the image is plotted on it. It returns the plotted images on its final line. The code establishes the necessary libraries and functions for displaying and plotting images using Jupyter Notebooks and defines a function to plot batches of images. Python code to copy files from Google Drive to a Google Colab directory using sent TensorFlow version 1.x. In the first step of the code, the directory is changed to the specified folder in Google Drive. A specific file format used for saving neural network weights and biases is ganchecks.tf.npz, which is copied from the current directory to the Google Colab content directory by using the commands sentcp and sentcp. Sentcd is used to change the directory to the content directory. This code uses the sent TensorFlow version command to make sure TensorFlow is being used at the correct version. As a summary, this code transfers files from Google Drive to Google Colab and sets up an environment to run TensorFlow. It imports the Python files GAN PyTorch within the CS231N directory and its functions and variables. Now you can use any variable or function defined in the GAN PyTorch file within the current file. Imported functions are preprocess.img and deprocess.img, which are useful for preprocessing and deprocessing images for generative adversarial networks. In addition, rel_error is a function that calculates the relative error between two sets of data. To count model parameters, there is a function countParams. A dictionary is also imported from the file gancheckstf.npz, which is the variable answers. Tests or validations of the implemented GAN model are likely to be conducted with this file. In this file, pre-computed answers or solutions are provided for comparing with the results of the GAN model. A useful feature is that it can be used to debug and check that the model is working correctly. NumPy's mp loads the dictionary from file to mp.load gancheckstf.npz. Result, this function loads the saved data from a .npz file into a dictionary where the keys represent the names of the saved data and the values represent the actual data. This code imports the necessary functions and variables for implementing a GAN model and loading pre-computed answers for testing and validation. A variable numTrain with a value of 5,000 is defined, and a variable numVal with a value of 5,000 is defined. The training and validation datasets are sorted by the number of samples in each column. A noise vector that has 96 dimensions is defined next with the variable noiseDim. Afterward, the variable batch size is defined with the value 128, which indicates the number of samples that will be loaded simultaneously in each batch. Next, mnist dataset is loaded using dset.nist with the specified directory and transform function. When a dataset is selected for training, the data is downloaded if it has not already been saved. The data loader with the dataset and batch size is created next, as well as a custom sampler called chunk sampler. An array of chunks from a dataset is randomly sampled using the chunk sampler class. The same process is repeated for the validation dataset, creating another data loader with the corresponding sampler that will randomly sample a chunk of data from the validation dataset. By using the functions iter and next, the first batch of training data is retrieved from the data loader. As a next step, the data is converted into a NumPy array, reshaped to have a batch size of 128 and flattened to have dimensions of 7 and 84. Show Images displays the batch images using this data. Each batch in the dataset is processed in this manner. From the package CS231N, the function sample noise is imported from the module GAN PyTorch. Sample noise takes in two parameters, batch size and dim. It is determined by these parameters that the output will be a tensor containing random noise values. For reproducibility, PyTorch's manual seed is set to 231. Afterwards, the tensor is converted to a NumPy array, which is checked for shape and range within the desired range. Upon completion, a message indicating the success of all tests is printed. To ensure that the random noise generated by the sample noise function meets the desired criteria, this code generates a batch of random noise. From the file GAN-PyTorch.py, we import flatten, unflatten, and initialize weights. Using the first two functions, you can flatten and unflatten data, and with the last, you can initialize the weights of a GAN model. Since the code only imports these functions to use them in another program, it does not perform any action on its own. As a result, it suggests that some of the code for which it is being used involves the creation or training of a GAN model. Python code assigns variable dtype to typetorch, float tensor. As a result, any variable with this type will be a floating point tensor. There is a comment outlining the next line, which means it will not be executed unless the comment is removed. A remove of the comment will instead replace the variable dtype with torch.CUDA float tensor. Using this type, GPU-calculated tensors are greatly sped up when performing calculations. In this code, the discriminator function is imported from the CS231N package. Defines a new function, testDiscriminator, with a parameter trueCount, a value of 267,009 by default. A variable model is created by calling the discriminator function within the function. As a result of this model, we will be testing the discriminator network. A number of parameters is then returned from the model by calling the countParams function. A value of this type is stored in the curCount variable. This is followed by an if statement that compares the variable curCount to the optional parameter trueCount. Discriminator parameters are incorrect if they are not equal, and an error message is printed. This will print a message stating that the parameters are correct if they are equal. Last but not least, the testDiscriminator function is called without any arguments, which runs the function using the trueCount default value and prints the appropriate message. From the CS231N.GAN PyTorch module, the generator function is imported. In addition, a testGenerator function is defined, which takes a parameter trueCount with a default value of 1858320. The function initializes the generator with a batch size of 4 and counts the parameters. An error message is printed if the current count does not match the true count, indicating that the generator architecture may be wrong. If there is no error, a success message appears. As a final step, the testGenerator function will be called without any parameters, resulting in the value 1858320 being used as the true count by default. For proper functioning of the GAN generative adversarial network, this code ensures the generator has the correct number of parameters. From CS231N.GAN PyTorch, import BCE loss, discriminator loss, generator loss. 3 functions from the CS231N.GAN PyTorch module are imported. In the code, these functions will be used later on. In the next line of code, def test discriminator loss logits real, logits fake, dloss true, a function test discriminator loss is defined. It takes 3 parameters, logits real, logits fake, and dloss true. The following line, dloss equals discriminator loss torch.tensorLogitsReal.typeDtype, torch.tensorlogitsFake.typeDtype.cpu.numpy calls the discriminator loss function and passes in the two arguments torch.tensorlogitsReal and torch.tensorlogitsFake. In the code, the .type converts the tensor data type into the D-type specified earlier. A NumPy array is created and assigned to the variable dloss when the pu.numpy runs. As the next line states, print maximum error in dloss, gsent rel error dloss true. Dloss prints out the maximum error between the expected dloss value and the calculated dloss value. Using rel error, which is not defined in the code snippet, this will cause an error. Using the last line in test discriminator loss answers, logits real, answers logits fake, answers dloss true by passing 3 arguments from the answers dictionary, the function test discriminator loss is called. A function like discriminator loss could be tested with these values, but they are not given in the code snippet. The function test generator loss takes 2 inputs, logits fake and gloss true. First line in the function creates a new variable called gloss. Gloss is calculated by passing logits fake through generator loss. The logits fake tensor is converted to a NumPy array and converted to a tensor of type D-type defined elsewhere in the code. It uses the real error function, which is also defined elsewhere in the code, to calculate the maximum error between gloss true and gloss. Last line of the code calls the test generator loss function with 2 inputs, answers logits fake and answers gloss true, presumably to test the generator loss function's accuracy. In summary, this code computes and compares the generator loss between predicted values logits fake and true values gloss true and prints the maximum error. This code imports 2 modules from the CS231N package, GAN PyTorch and run a GAN from the GAN PyTorch module. You can use the getOptimizer function to obtain an optimization function for training a generative adversarial network GAN. To generate realistic data, a generator and discriminator network are trained to compete against each other in the run a GAN module. A PyTorch framework is used for training a GAN using the code. To assign the type to the D object, this Python code first creates a discriminator object using the discriminator function and assigns it to the variable D. In the next step, it creates a generator object using the generator function and assigns it to the variable G. It also assigns the type of the generated object based on the specification of the D-type variable. In the next step, it calls a function called getOptimizer with the discriminator and generator objects passed as arguments. The function returns optimizers for both the discriminator and generator, then assigns them to the variables dsolver and gsolver, respectively. A loader train object, a discriminator object, an optimizer object, and loss functions for the discriminator and generator are sent to the run a GAN function. The discriminator and generator are used to generate images using GAN Generative Adversarial Network. After the function returns the images, they are assigned to the variable images. A 0 is assigned as the initial value for the variable numiter in this code. In the next step, it loops through a list of images and outputs the currently selected image's numiter value and calls a function showImages. The next line displays the image using the plt.show function. Thereafter, numiter will be incremented by 250. Each image in the sequence is displayed until the entire collection has been displayed. Lastly, the printer prints an empty line. Most likely, this code displays a series of images with a specific interval between them. Generated Adversarial Network GAN model output image is visualized by this Python code. As a header for the image, following the code prints vanilla GAN final image. After that, the function showImages is called, passing the variable images nice1 as a parameter. As a result of the GAN model, this variable represents the final output image. Displaying the image on the screen is accomplished with this plt show command. In this code, the user can visualize the final results of the GAN model training. There are 2 loss functions provided by the module cs231n.ganpytorch that are imported here. Afterwards, it defines test lsgan loss, which takes 4 parameters: score real, score fake, dloss true, and gloss true. It converts the score real and score fake inputs to tensors and then uses them as inputs for the discriminator loss and generator loss functions. After converting the outputs of these functions into NumPy arrays, the loss and gain variables are created. In the end, the function displays the maximum difference between the dLoss_true and gLoss_true values compared to the dLoss and gLoss values. Using this code, you would need to provide values for the scoreReal, scoreFake, dLoss_true, and gLoss_true parameters, and call the test ls_GAN_loss function. A comparison of output values with the expected values provided for dLoss_true and gLoss_true is used to test the accuracy of the discriminator loss and generator loss functions. Assigning a discriminator and generator to variables dLs and gLs starts two models. In this step, the models are converted to a specific data type indicated by the d-type variable. By using getOptimizer, the code creates two optimizers for the discriminator and generator models. Using the images variable, we can store the output of the run_a_GAN function, which takes in the discriminator model and the generator model, plus their respective optimizers and loss functions. The GAN generative adversarial network algorithm is used to train the discriminator and generator models as adversarial systems. Essentially, the discriminator tries to classify the generated images as fake, while the generator attempts to create more realistic images to deceive them. By combining these two processes, realistic images are generated that are indistinguishable from the real thing. Following that, the code returns the generated images based on the GAN. Using a for loop, this code iterates over the image list. With each loop iteration, num_iter is incremented by 250 from 0. A format method is used within the loop to insert the value of num_iter into the string to show the current iteration number. After calling the showImages function, the current image is displayed before being displayed by the plt.show function. Every time a new image is printed, a blank line is printed between the previous ones. The process repeats until all images are displayed. In this code, the final image of an ls_GAN model is displayed using print, showImages, and plt.show. Aim is the last element of the images list passed as a parameter to the showImages function on the second line, which prints the text ls_GAN final image. The image is displayed finally with the plt.show function. The ls_GAN model output can be visualized using this code. From the CS231N package, a function called buildDCClassifier is imported. After that, a variable called data is created by enumerating a variable called loader_train, and then taking the last element of that result and the first element of that element, and casting them to a specific data type. Afterward, the buildDCClassifier function is called with batch size as a variable input, and the result is cast to B's data type. Following that, it performs some operation on the data variable and stores the result in a variable named out. Last but not least, it prints the size of the out variable. The code basically uses the buildDCClassifier function to create a neural network model, which is then used to predict data values. As an input, the batch size is used to customize the model, and the data variable is used for training or testing the model. Model predictions are stored in the out variable, and its size is displayed. TestDCClassifier, a function defined in the code, has a default value of 1102721 for true count. Following this, a function called buildDCClassifier is invoked, and the result is assigned to the variable called model. It then counts the number of parameters in the model and assigns the result to a variable named curCount. This will print a message stating the generator does not have the correct number of parameters if curCount does not match true count. It will otherwise print a message indicating that there are the correct parameters. The final step is to call the function testDCClassifier. In general, this code checks if the number of parameters in the model matches expectations, and if there is a mismatch, it alerts the user. In this code, we import buildDCGenerator from CS231N.GAN PyTorch. Using the PyTorch library, this function generates a generative adversarial network GAN. In the type code, you specify the data type that the generator will use. Afterward, the buildDCGenerator function is called, with the result being assigned to the variable testGGAN. Taking no arguments, the function returns a generator. This code then applies the initializeWeights function to the generator using testGGAN.applyInitializeWeights. When training the generator, this function is likely used to initialize the weights. Using torch.randn with batch size and noise dimension specified, the code creates a tensor of random noise. Generator input will be this. As the input to the forward function, the test GAN.forward_fake seed line passes in the fake seed tensor. On the basis of the random noise input and the weights initialized previously, fake images will be generated. Lastly, the code prints the size of the thwart fake images tensor, which provides the dimensions of the generated images. It depends on the batch size and the generator's settings. There is only one parameter in this code, true count, which is set to 658801. It creates a function called test_DC_generator. Using the build_DC_generator function, a model is created with the parameter of 4. It is then used to determine the number of parameters in this new model, and this number is stored in the variable curCount. Following that, the code validates that curCount equals true count. An error message is printed if the parameters are not equal, and a suggestion is made to have a look at the model architecture if they are not equal. A message is printed if the number of parameters is correct, if they are equal. With no arguments passed to the function uses the default value for true count and executes the code, which prints the appropriate message depending on the comparison between curCount and true count. This Python code is part of a program that implements a generative adversarial network GAN. A GAN is composed of two neural networks, a discriminator DDC and a generator GDC, which compete against each other to generate realistic images. A discriminator network is created and returned using a function called build_DC_classifier, which is called by the code first. As a next step, we cast the discriminator into the specific data type dtype. The next line calls an initialization function, initializeWeights, to set the discriminator's initial weights. Weights determine how the discriminator evaluates images generated from the generator, so this is an important step. For the generator, the code performs a similar process. This function creates and returns a generator network by calling build_DC_generator. We also cast this generator to the specified data type and initialize its weights. The code calls two functions to get each network's optimization objects once both the discriminator and generator have been set up and initialized. Optimizers update the network weights during training. Lastly, a function called runAGAN is called, containing both discriminator and generator networks, their respective optimizers, loss functions, and training data loads. Using this function, you can train your networks for 5 epochs and get the generated images as a result. This code initializes and sets up a GAN in Python, including a discriminator and generator network, as well as their respective optimizers and weight initializers. It also returns the generated images after training the GAN for a specified number of epochs. To begin with, this code creates a variable called numIter and assigns it a value of 0. With the for loop, the program loops through a list of images, assigning each image to a variable called img. During the loop, the code prints the iteration number and then calls showImages, which takes the current image as a parameter. A picture is displayed presumably by the function. Immediately following the function call, the plotting library or tool is called again to display the image. The code then prints a blank line after incrementing the numIter variable by 250. Here, an image list is looped through and displayed one by one, with 250 iterations accumulating at every iteration. Using a deep convolutional generative adversarial network DCGAN to generate images is demonstrated in this code. To start, simply print out DCGAN final image to the console. Next, a function called showImages is called with a list called images as an argument. Last but not least, the last line calls a function called plt.show that displays the image. Using this code, we can see the final DCGAN generated image.